There are many similar techniques in SGD, like SVRG. We can reduce the variance of stochastic gradient. For instance, in SAG algorithm, stochastic average gradient, shortly SAG, we update xt plus 1 like this, xt minus some step size comma k over n summation I1 to n. Here we add yi at t, so yi vector is time dependent, and yit, we every time we update yit equal to gradient of fi xt if the index I is the randomly selected index. Otherwise, we keep the last time y vector. Okay, but in this case, unfortunately, the expectation of 1 over n summation I1 to n yit is not equal to the gradient of original objective function at point xt. But still, we can show that this update rule can converge to the optimal solution x star. And this update rule indeed reduces the variance a lot. So when you think the variance of 1 over n gradient sum of yit, since there are 1 over n term here, and only one part is random stochastic gradient, the variance of this summation is very, very tiny. It's proportional to 1 over n square. Okay, so because of this nice property, we can make a theory, fast convergence theory, although that proof is very, very complicated. So one simpler version of SAG is SAGA. So for alpha strongly convex and beta smooth function, we update WT plus 1 is equal to xt minus step size gradient of fit xt minus yit t minus 1 plus 1 over n summation I1 to n yi t minus 1. So like a SAG algorithm, yit vector is updated to gradient of fit xt if I is the selected index. Otherwise, we keep the last time y vector. So basically, SAGA algorithm essentially combine the idea of SVRG and SAG paper. So we basically make this update rule is unbiased gradient estimator. And also because of this update rule, we can reduce the variance as well. Okay, and why this is not xt plus 1 but wt plus 1? Basically, this paper considers proximal gradient descent approach. So when we have additional cost function h, we have to use proximal gradient with h cost function and step size comma with this update rule. Okay, then this update rule will converge to the optimal solution of this total function fx plus cost function hx. Okay, and the theory of SAGA paper is this. When we set gamma is equal to 1 over 2 times alpha times n plus beta, then the conversion speed is proportional to 1 minus alpha over 2 times alpha n plus beta per 2k after k update. Okay, so when we want to make a epsilon close property, so when we want to fx minus fx star less than or equal to epsilon, then the k value should proportional to n plus kappa, the conditional number kappa, times log 1 over epsilon. Okay, so this is a little bit confusing notation, so let's say t. So the number of iterations should be proportional to the total size of your fi, the how many function in your original total function f, and also it depends on the condition value kappa. But when you compare with original gradient descent rule, the vanilla gradient descent rule without any stochastic gradient, when we have alpha strongly convex and beta smooth function, the conversion speed roughly kappa times log 1 over epsilon. If you want to the same epsilon accuracy performance. But remember that the full gradient require n number of gradient computation because there are n number of FIs. Okay, so the true conversion speed must be n times kappa times log 1 over epsilon. So this SAGA update rule essentially changed this n kappa to n plus kappa, which essentially use less iteration compared to the full batch gradient descent algorithm. Okay, and also if you compute the epsilon convergence behavior of SVLG, you can observe the same behavior. You can notice n kappa log 1 over epsilon is changed to n plus kappa log 1 over epsilon using SVLG and SAGA. Okay, so these two stochastic gradient distance rule, so not only just for real invention for stochastic gradient descent, but this essentially actually gradient boosting techniques kind of, which can make your update rule spend less computation with less memory space indeed. Okay,